Now let's start with binary logistic regression. How do we run the main analysis of binary logistic regression? So the first you go to regression, you go to binary logistic, and let me reset that. So as you remember, we can do the binary logistic regression only if our dependent variable, we have a version of our dependent variable that has only two levels. That here, this version of depression, that is my dependent variable, can be suitable for this assignment. Because you see depression level binary, that is has only clinical and non-clinical levels. So I put it here. This is my dependent, I can see dependent variable. And I set my independent variables all to covariate section. Covariate, as I said, in this context, covariate means predictors. And so I don't have any categorical predictors, so I leave this box. It doesn't matter. In save, this is the part that I talked about influential outliers. So if I tick cooks in this part, it can help me to check if there is any influential outliers in my data that can influence this specific regression model. So I just click on this, okay. So again, save, cooks, continue. And then I go to options, and there are a few options that is not ticked by default, and I want to make sure that uh, they are ticked. So here in options, I go to classification plots and CI for uh, B, that is actually the odd ratios that I want confidence intervals for odd ratios. And finally, I want to Hosmer-Lemshow, if I pronounce it correctly, for goodness of fit, that can give me some measures of whether my model is fit or not. Uh, there is nothing else that you need here. You also, potentially you can also take correlations of estimate to check the multicollinearity, but you also can check the multicollinearity using the correlation option of your analysis. So it doesn't matter. So that's why it's not a big deal to tick it or not tick it here. Because anyway, you can check the bivariate correlations between your IVs, like if you check the correlation analysis in SPSS. So that's all good. So these three options, you make sure that they are ticked, you don't change anything else and continue. And that's all you needed for your analysis. And if you click on OK, before going to the main analysis, I also want to check the final assumption that we couldn't check beforehand, and that is the influential outliers. So you see that after clicking for running the analysis, a new column emerged here, and that is for Cox distance. Cox distance, what does these values mean? These values that you see that there is a value for each participant. If there is any participant who has a value equal or greater than 1 in this column, that means that that participant is potentially an influential outlier. But as you can see, I have no participant with coexistent above 1. You see that all of these values are below 1. And that means that I don't have to exclude any of my participants from the data. Even if they are shown as outliers in my descriptive statistics, the coexistent result shows that there is no outlier in my data. So I don't have to exclude any participant based on this ground. So that was the assumption, one of the assumptions that I couldn't, I could actually check before even run the analysis, but the main analysis allowed me to check this assumption alongside with the main results. So now in the output, the first point is that you don't need to check the block 0 type of output. You go straight to block one because this block one is the relevant results to your hypothesis testing. And in block one, the first thing that you want to check is the omnibus test that should be significant for model. So you can report the chi-square and like after that. So the first thing is that you see that the chi-square that is actually relevant to the model and the significant of chi-square, and it can show that your model is significant, like your general model as like in a general pattern of the predictions that you design in this model is significant. We still don't know if individual predictors can have a significant contribution or not, but we know that this package together, like this package of this pattern of predictors together, uh, can be a significant pattern of predictors. And so and the next part that you want to check, actually, before going to this sort of R squared, I'm going to another chi-square value that is actually have a completely different interpretation, and that is Hosmer and Lim show that unlike the previous one, this chi-square in this table, should not be significant. So if it's not significant, actually, it can show that your model is fit. That means that the arrangement of your variable in your model is statistically sound, statistically robust or fit. Although this is also based on chi-square, but the interpretation is the opposite of the previous one. So here we want the chi-square not being significant because it's a fit index. It's not actually, it's a model significance index. So here the chi-square should be significant for the model, but here ideally the chi-square should not be significant. And you see that it's very good results for our model. And then we can go to interpret these results, that is actually the R square versions in the context of a binary logistic regression. So this table is pretty much similar to R square concept in a multiple regression model. Here you can either report Cox and Snail R square, or you can report the Nagelkerk R square. That's very hard to pronounce, but you know what I mean. And this one actually, they are both actually can be reported, they are both acceptable, and because there are just different alternative measures to show the general R square of your model. However, this one that is the hardest to pronounce, the Nagelkerk R square, is usually recommended to be a more robust measure of your omnibus prediction of your variable. So how to interpret that? So the R square here, like for example, if you want to report this one, the square here, it actually shows the percentage of the variance in your outcome variable that can be explained by all your IVs in the model in general. So as I said, it's pretty much similar to, or the same actually, I can say, interpretation that we have for a typical R square in a multiple regression. So like the same way that you see that the textbooks report or interpret R squared for a multiple linear regression model, you can use the same language to report that or interpret this R squared, like 49% of the variance of your DV can be explained with all of your IVs in your model. And so I explained this one as well. So the next, and soon after that, so you usually report this and directly then jump into your variables in your model, like variables in the equation, the last table. I will go back to the other tables later. But the most important one that usually in your results section, when you report this R squared, you usually need to immediately report the individual coefficients after that. So, so that is the variables that you have in this table. That is variables in the equation table. So in this table, B actually, this variables is equal to unstandardized regression coefficient. Like similar concept that you have a multiple linear regression. SE that is standard errors and wild stats here. The function of this statistic is just to check the significance of the regression coefficient. For example, the significance that you have here is not directly for B, it's actually for the wild statistic that is associated with B. Uh, so so rather than, for example, you report that B and significant, you actually should report B wild and then significant. It's pretty much like the function of T in like a typical a simple regression model that usually report the significance for the T that is associated with regression coefficient, not directly for the regression coefficient. So that's why you need usually to report wild associated with the significant level in addition to the unstandardized regression coefficient. And so the next thing that I wanted to explain, yes, I think the other things, like a standard error is not very important. If you want to skip that in your report, that's okay. But this column is the most important statistic that actually you have in this table, in addition to actually the confidence intervals. This column, that EXPB, that actually represent your odd ratios that you see all the papers or the studies using logistic regression, they usually report odd ratios, especially if a binary logistic regression. Uh, these are like this statistic in this column that we call them odd ratio are the most essential values for your hypothesis testing. So if your odd ratios are less than 1 or more than 1, uh, that means that there is a higher possibility of actually to be significant. If your odd, the more, the closer your odd ratios is to 1, that is the less possibility of significance. So if you see a very small number here, like 0.05, that's actually a very large effect that you have. So we are just concerned about the values that are very close to 1, because 1 here is the measure of lack of significance. That means there is no difference. So let's go a little bit to details of how to interpret these odd ratios. So in general, odd ratios less than 1 or more than 1 likely to show, as I said, a significant prediction. And they are significant, the odd ratio, if significant, if the confidence intervals does not include a value of 1. So, and usually it's very consistent with the significant that you can see here. But as an additional measure of significant, you also can check confidence intervals. For example, both levels of your confidence intervals should be either less than 1, like here, for example, you see both levels, lower band and upper band are less than 1, and which is consistent with here, and that means that this odd ratio is significant. Or both levels should be higher than 1. Like for example, the lower bound and upper bound here is higher than 1, and we can see that the regression coefficient is significant, and the odd ratio also we can say that it's significant because it doesn't include 1. However, for this one that you see that the regression coefficient is not significant, you can see odd ratio also is not significant because the lower bound is lower than 1, but the upper bound is higher than 1. That means that the range includes 1, and that is the measure that we can say that the odd ratio is not significant. Another consideration for odd ratio is the direction of odd ratio. And For example, and also as I said, this is very just before going to the direction, you can see that the confidence intervals are usually consistent with the significance of WALT that we can see here, like WALT ratios. It's rare that we can see any inconsistency here. So how about the direction? So if in terms of the direction, so one tip that you have, again, the easiest way for direction is that you check the direction of the regression coefficient. Like if it's a minus, that means that higher levels of your IV actually can reduce the odds of uh, your outcome variable, that, for example, the participant being in clinical levels of depression. However, there is also another way that you can interpret the direction of your odd ratio. And that is if your odd ratios are less than one and they are significant, like for example, for this one, the first one, that is less than one, and also is significant because it doesn't include one in that variable, that means that there is a reverse way of prediction. That means that the higher levels of your IV can predict lower possibility of your DV. But if the odd ratio is higher than one and it is significant, like here, that is significant, the confidence interval doesn't include one, and also because it's higher than one, both bounds, and also it is higher than one, the odd ratio itself, that means that there is a direct relationship, direct and positive relationship. And as you can see, this is also very consistent with the direction of effect that you can see in your coefficient values here. So, and also just quickly also see that how you can interpret that. For example, for the significant one, that is, you see a negative coefficient and is significant. Remember what was our DV? Our DV was clinical versus non-clinical levels of depression. And the way that I coded that DV was that the zero was like non-clinical level and a one was clinical level, that I can maybe show you in the data output as well. That this is the DV that I included in the uh, like binary that I included in the analysis. That if I don't label it, you can see it's a 0 and 1. That 0 is non-clinical, 1 is clinical. So considering that, when I come to this table, a negative regression coefficient and odd ratio less than 1 can show that the higher levels of my IV1 can actually reduce the odds of clinical depression, because you remember the 0 was non-clinical, 1 was clinical. That means that the positive relationship would increase the odds. But here decrease. For example, that means that my IV1 is a protective factor. For example, it can be the higher levels of social problem solving, that when it's higher, the odds of having clinical levels of depression is lower. How about this one? You can see that this FX also is significant and the odd ratio is above 1. That means that there is a direct and positive relationship. So in this case, I can say that higher levels of my IV4 can significantly increase the odds or the likelihood of having a clinical depression. So in that case, we can see it's very informative data and very easy to interpret. So this is the way that you interpret your data. And if you want to be more precise, it's not necessarily you cannot see that in all the publications, but it is an optional step that you can. That if you want to present um, uh, also, the change in odd ratios in percentages, there is an option for that. For this, you can subtract each odd ratio from 1 and multiply the results by 100. This will give you the percentage of change in odd ratios, that in odds that are associated with 1 unit increase in the predictor. I know that is confusing. Let me to explain that with one example. For example, for IV4 that we have here, if I do this process, like for example, I subtract the odd ratio from 1, I multiply this odd ratio by 100. Uh, the odd ratio that you can see, for example, here is 1.043. That means that uh, in this case, if I do that, do that like calculations, the number would be 4.3%. Then I can interpret that each unit increase in IV4 uh, can significantly increase the odds of clinical depression by 4.3%. So 4.3 is the percentages that I achieved out of that calculation. That again, another time I repeat that. I can interpret that in this way that each unit increase in IV4 can significantly increase the odds of clinical depression or clinical levels of depression by 4.3%. So that is the way that you can interpret the result. As I said again, it is an optional step. You don't see that in all publications that's reporting that. What I mentioned before that like saying that higher levels of IV4 is significantly increasing the odds of clinical depression, like and reporting these statistics that also acceptable to test your hypothesis. So this is the main things that you need to report for your hypothesis testing. However, there is an addition. You can also ignore this table. It's not very informative for your hypothesis testing because you have everything for your specific hypothesis here and here, like based on the general R squared and model fit. However, the classification table also can be a useful data to report. If you have a space in your results section, you also can report that. Again, this is not something that you typically see the papers report, but you can also, if you want to include that in your data analysis and your results section as well. So how to interpret that? So as you can see, this table can show that how your predictors, uh, like the predictions that you have in your models can match the actual observed categories. It's very similar to like for example, some uh, frequency analyses that you can see that, for example, if you have the prediction about a proportion in a population and you want to see that if this prediction is matching the actual data. So it's something similar to that that you can see in some non-parametric statistics. But here, actually, as you can see, it can show that how precise our prediction of the categories, like the categorizing our participants based on the category of the dependent variable is precise, based on this analysis. So the table can give you two measures. Like what we call as sensitivity and what we call as specificity. Sensitivity refers to the true positive rays, that how precisely we can detect the true positive. So positive and negative in this context is very similar to what these terms means in the context of medical sciences. For example, when you do a medical test, if they said that the test is positive, that means that you have that disease, that the disease that you tested for. When you say that is negative, that means that you don't have that test. So sensitivity means that when, for example, a participant should be falling through the clinical levels of depression that we have here, like having the mental health problems that we are looking for, and our results and our analysis actually could precisely detect that. So this is the levels that we say sensitivity. That here is 62. for us. That you can say that sensitivity rate for our analysis is 62%. That means that we can, for 62%, we can correctly detect the clinical levels of depression in our sample. The other one is specificity, that is about the true negative rates, that how correctly we could detect the negative outcomes, like the participants who don't have clinical levels of depression, we could correctly detect that they don't have the clinical depression, and that is 87% for our result. That means that for 87%, 87.8%, we could correctly detect those participants who should not fall into non-clinical category of depression. And both are acceptable. And we have also an overall percentage, that is overall accuracy of our prediction in general. So in overall, we could, for around 78.5%, we could accurately categorize participants in correct categories based on this model of predictors that we included in this model. This can be, so this table is called classification table for this uh, like in our output, but in some other softwares and output views, it might be named with other names that I will explain in other videos. So that was all you needed to know about binary logistic regression. And as long as you know this concept, like for example, the coefficients, world, like odd ratios, confidence intervals, and how to interpret that, this is pretty much how we interpret the other types of logistic regression as well. So, and I'll show you now that how similar they are with just very slight differences. For example, now let's go and check the ordinal logistic regression. So again, the first things to check is that we can go to ordinal logistic regression if we have a variable like this. For example, a variable that is categorical, that has more than two categories, and you can assume a natural order between the categories like mild, normal, severe, extremely severe. So in my ordinal logistic regression, I no longer can include this version of my DV because it has just two levels. I should include this version of my dependent variable that has more than two levels and can be considered as an ordinal categorical variable. So for ordinal logistic regression, you can go to regression, ordinal, like in this part. So let me reset that. So you send your ordinal version of your dependent variable here, and then you send your all the continuous variables that you have, like IV1 to IV4, to covariate. Again, the context of covariate means what you need actually, your continuous variables. And in options, there is nothing that you need, but in outputs, there are some parts that you need to tick. So just make sure that they are ticked already, like these goodness of fit, summary, statistics, parameter estimate, make sure that they are ticked, that usually they are ticked by default. The other thing that you want to tick is a predicted category and also test of parallel lines. So this is about the only assumption that is specific to ordinal logistic regression. So, but it can be very easily checked. If you just tick this box, so it will check this assumption for ordinal logistic regression. That is called test of parallel lines. So that's all you need for like your analysis, and then continue. Nothing else you need to change. It's all good now, and we can go to our main analysis. So for model fitting information, that is your first table, and also for the next one, that is good fit, good of a fit, it's very actually similar to what I mentioned for the binary logistic regression. Uh, in summary, you want a significant chi-square here, like in model fitting, that is about the likelihood, that is model fitting here for the final. You need to report chi-square and the significant, and it's very ideal. You want it to be significant. However, uh, this is, however, here you don't want to be significant. Also, you check it specifically for deviance, not for Pearson. Although Pearson also can be similar, but deviance is more reliable to be checked for this content. So this row you can call the chi-square for the deviance row, and the significant that we want it ideally not to be significant. So if it's not significant, that means that your model is fit. The interpretation is pretty much similar to what you had for uh, binary logistic regression. And and then you go to like the pseudo R squared. So here we call it actually pseudo R squared. And this is but it's still very similar to all the statistics that you had, and it's the same that you would interpret that for your binary logistic regression. Like pseudo R squared, this table also is interpreted exactly the same way that I just explained for a binary logistic regression, that you can apply all the points, all the wording or the way of interpretations for this number here. That again, the middle one, I would suggest that this is the more robust one to report for your omnibus test. And the next table, that is the first, the very main one that you can test your logistic regression based on, that is actually the this table. And in this table, what you need to check is this one, the second part of the table, that is about location, not about the threshold. So here in location, you can see the names of your variables that for each of your variables, and everything is similar to what I just discussed for the binary logistic regression. Like estimate here means that the on a standardized uh, coefficient, on a standardized coefficient for each of your variables, a standard error that you know that you use a WALT for the checking the significance of each of your coefficients alongside with the significant. So, but unlike the binary logistic regression, you don't have odd ratio anymore here. So you just report the your main coefficients and WALT and significant. And interpretation was but a little bit it's still similar, but has some more nuances compared to binary logistic regression. Because remember that your dependent variable here is ordinal. That means that it started from like normal depression to mild to like moderate, severe, and extremely severe. So if you have a significant coefficient here, you first check the direction of that coefficient. For example, let's just start with the positive one that is easier to interpret. For example, IV3 has a positive prediction for our ordinal dependent variable here. What does it mean? So it means that higher levels of IV3 can significantly increase the odds of higher levels of your dependent variable. That means that it can increase the odds of having a more severe level of depression, or more elevated level of depression for your participant. That means that if we have higher levels of IV3, our participants are more likely to have a depression level that is closer to severe levels compared to normal levels. And that is the only different uh, interpretation that we have compared to binary, because it's more than one category. It just can show that there is a higher possibility that our participant can have the elevated levels of depression if this variable, if you have higher levels of IV3. And it can be the opposite for IV1 because it's a negative relationship and it's significant. That means that IV1 can be a protective factor. Like, for example, if it's social problem solving, that means that higher levels of social problem solving can decrease the odds of having elevated levels of depression. That means that the participants are more likely to fall into the lower levels, lower categories of depression, like for example, normal or mild compared to like severe or extremely severe. And I'm just checking if anything else I can add to help you to interpret this table. As I said, estimate is on a standardized regressions. Also, just take it into consideration. So, and again, another time, let me, for example, if just I maybe another review would be good. For example, for the positive and significant relationship in this table, you can say that this positive coefficient indicate that higher scores on this certain predictor is associated with greater likelihood or greater odds of being in a higher category of depression levels. Like for example, here is depression. A negative coefficient is the opposite of that. So you can word it in any way that can convey this meaning that, as I said, the most conservative way would be saying that like higher levels of this variable is associated with elevated levels of or higher levels of like depression or higher categories of depression or elevated categories of depression. And the last one that actually you could check it first, and it is about the assumption of parallel lines. So this table can help you to test the assumption of parallel lines. And as I said, this is unique assumption for this type of logistic regression that is just ordinal logistic regression. So it's very simple to interpret. If it is significant, that means that this assumption is violated. If it is not significant, like here, that means that the assumption is met and we can confidently interpret our data. So what if it's significant? So if it is significant, you can either change your model, like for example, maybe you remove some of the variables from your models and see that if the model can work better and it can be non-significant, if, for example, you remove the insignificant variables from your model, or you can also run the multinomial logistic regression if this is violated, because it's one of the signs when it's violated, it can show that there might not be a good order between the levels of your IV. That means that maybe, for example, your uh, uh, like uh, depression levels, maybe you need to compare them one by one. Like, for example, comparing the extreme level, the severe level to normal levels separately, not necessarily based on an ordinal level. That I will explain that in the ordinal multinomial logistic regression shortly. So in general, if it's like this, is okay. You don't need to do anything, but if it's violated, you may want to run a multinomial logistic regression. However, in general, I would recommend you to run, if you want to use ordinal logistic regression, I would recommend you to associate that with a multinomial logistic regression because it can give you a better picture of your data. But if you want to run the multinomial logistic regression, we can just do it for the significance variables here. For example, if your IV1, IV3, and IV4. You can just exclude, for example, IV2 if you liked for running multinomial logistic regression. Because multinomial logistic regression can give you more statistic. For example, you don't have odd ratios here, but that can give you odd ratios. And also that can give you more specific comparison that I can show you now how it can be more helpful. But it should be associated with ordinal logistic regression in this context because our variables can can be assumed as ordinal, but so that's why you should always first do the ordinal and then move to multinomial if you want to do this arrangement of analysis. So for multinomial logistic regression, again, for the assumptions, it's very similar to the ordinal logistic regression. You should have a categorical variable that has multiple levels, more than 2 levels. So in that case, you can run the multinomial logistic regression. And also it can allow you to have pairwise comparisons between categories when investigating the effects of each IV on your outcome variables. So let's try that. Again, you go to regression, you go to multinomial logistic regression. Let's to reset that. So you send the version of your IV like here that is that is actually has multiple levels, and you also put all of your sorry, it was DV actually. And you put all of your IVs to covariate because they are continuous variable. If they were categorical, you would put it in factor. And the first thing that you need to change, you may want to change this part. Let me explain what does it mean first. So reference level category is that because when you run a multinomial logistic regression, it will compare the effects of each of your IVs for different levels of your DV. For example, it can compare let me show that based on here. For example, it can show you that if the higher levels of your like IV1, uh, sorry, the IV1 can increase like the odds of having severe levels of depression compared to mild levels of depression. So it can do this by pairwise comparisons in your analysis. However, it can do this to just one of the levels of your DV as the reference. For example, if I consider that like change it first category here, and do it continue, that means that all of my analysis is going to be compared, all the levels of your DV are going to be compared with the normal level, that is the level 1 of your DV. For example, uh, it can show that if your independent variables can increase the odds of mild versus normal levels. It can also show that if they can increase the odds of severe versus normal, the odds of moderate versus normal. So normal is the reference for our comparisons. It will make better sense when I show you the actual output. But just for now, for my type of data, it would work better if I change it to the first category because I want that the normal levels of depression would be the reference for comparisons. So I put continue. The next things I want to change is to check that if everything in the statistics are okay. So here in the statistic, in addition, just make sure that all of these are ticked, that by default should be ticked, but just double check that all of these areas are ticked. And also I want to, in addition to that, maybe going for goodness of fit, because having like some measures of model fit for my general model. And maybe I want to go to information criteria and also see that if anything else that I want to do now. Just about the classification table. I can actually tick that here, but I don't recommend that. I would recommend just including classification table for binary logistic regression because it's very complex to interpret for for multinomial logistic regression, and it also doesn't give a lot of helpful statistics, and that's why many publications also don't include this in the analysis. So I think all is good now. So we have everything that we need here to test our results and continue. And for criteria, definitely nothing else that you need to do. And also for save, also as you see that unlike the binary logistic regression, we don't have coexistence here. So nothing else. So that's all that you needed to do for multinomial logistic regression. So the first thing that you want to check is model fitting information. So in this area, in this table, you want to have first a look at AIC and BIC measures that they don't have any significance actually here, but generally we expect them to be not in large numbers. So it can be maybe with one model they are not very helpful, but if you, for example, run multiple models like different combination of your variables, the models who have lower values of them that like in the final one, the model with lower values here actually can be considered as a fitter model. And the other things that you want, and also the other points that you can also you are interested to check here is the likelihood ratio test that is very similar to what omnibus test that you had in other logistic regression. That ideally you want it to be significant. So significant chi-square here just for your omnibus test of your general model. Lower values we expect here. If you have like multiple models, you can compare, but you don't have significance for that. And here, for goodness of fit, again, deviance is what I recommend. It's very similar to what I said for ordinary logistic regression. In an opposite, it's the opposite of this one. You want this not to be significant. If it's not significant, that means that your model is fit. And again, this is very similar to what I mentioned already for the other two types of logistic regression. The middle one, the Nagel-Kerke, if I pronounce correctly. This one is the most robust one to for as your pseudo R-square measure, and that with the same interpretation that we mentioned for other variables. This likelihood ratio test, so in this also, it can be helpful, but usually not reported, maybe not in most of the published paper. In this table, we'd like to see significant statistics like for example, like what we wanted to expect here. So it's very similar to this, but just is divided for each of your IVs, each of for your independent variable. So if it's not significant, it still does not mean that you need to exclude your variables because your variables still can have something significant in the next table. But it can show you, it can be help with later decision makings. For example, if an IV does not have any significant impact, any significant effect either in this table and the next one, then we better to run the model again with removing that IV. And it probably would help to a larger pseudo R squared here and better model fit in these indexes if we do so. But anyway, it's not anything that I can say directly can inform your hypothesis testing. This table is the most important table for your hypothesis testing. So in this table that is parameter estimate, in each section of the table, one level of the DV is compared to the reference level. That you remember that the reference level that we determined in our analysis was normal, was level 1, that I show you another time, that for example, multinomial. I change it to be the first category. And the first category in my, based on the way that I coded my variable is normal. I coded normal as 1. So that's why normal is not presented here in this table because that is the reference category. So and this is the only difference, and everything is very similar to the binary logistic regression results. Like for example, you have B like on a standardized coefficients, a standard error world, the graph freedom, significance, and odd ratios and confidence intervals. But the way of the interpretation is a little bit different. So because you check each levels, you check the effects, you check the odd ratios for each levels of your DV separately, but the way of actually explaining that is similar. So let me like interpret one of them. For example, if we go to, we see that we don't have like, we have a significant result like for IV4 in mod. So how to interpret that? You see that it's a positive effect first because the odd ratio also is above 1. The coefficient, regression coefficient is positive and also is significant. So what does it mean? It means that higher levels of IV4 can significantly increase the odds of having mild depression compared to normal depression. That means that it's a pathological variable. That means that if this variable is higher, there is a higher possibility that the participant will have mild depression and not normal level of depression. So you see that here in the table, notice mentioned that the reference category is normal. That means that each of these parts of our tables, these categories, are being to compared to the normal variable, to the normal category. Like you remember in binary, we would compare just two levels to each other, but in multinomial, in each part of our analysis, we compare that category to the reference category that is normal. For example, let's me to interpret another level. Like for example, here we have a significant level again for IV4. That means that higher levels of IV4 can significantly increase the odds of having severe levels of depression compared to normal level of depression. That means that this is a pathological variable, that if it's, for example, it can be something like anxiety. Like if a participant have higher levels of anxiety, they are more likely to experience severe levels of depression compared to normal levels of depression. So again, is comparing just two levels with each other. That is very similar to binary logistic regression, but the point of our comparison is different in different levels. And so that's all. That's very similar interpretation to binary logistic regression. And the final point that I wanted to explain is what if you want to include covariate in any of these analyses? So it's very simple actually to include covariates in your analysis. And like, for example, let's just start to do with binary logistic regression. So imagine that you remember what we did for binary logistic regression, like putting our binary dependent variables here and the non-binary one here. You don't change anything about settings, so everything is set already because I just ran that analysis, so I don't change them. But the only thing that you want to change is adding another level to your analysis. For example, imagine that I want to run my analysis with controlling the effects of gender, marital status as covariate. So I put them in the first block of the, sorry, not here. I put them in the first block of my uh, prediction. And also in get categorical variable, I go and define them as categorical variable because they are both categorical. So I let the SPSS know that I want to consider them as categorical variable and continue. And then I click on next, and now I do everything like the way I did at the first place, like putting all of my IVs here. And in this way, my results will be adjusted based on the effects of this categorical covariance that I wanted to include. So if I click on OK, you can see that everything is the same. Everything that you have in your result is the same. But in this case, you are sure that you can rest assured that the effects that you have here, like the regression coefficients, the odd ratios that you have here, are adjusted, are controlled for the effects of the potential effects of your categorical, your covariance. For example, you are now sure that gender and marital status is not affecting this, like disregarding of interpersonal differences in gender, marital status, in depression levels. You can now make sure that your variables can robustly predict your dependent variables. And this is after taking to consideration, after accounting for the effects of gender and marital status. You also can see if they actually had any significant effect on your outcomes, that you can see that they actually don't have. That means that even if you wanted to exclude them from your model, that would be fine. But in this way, at least you are sure that they are not affecting your results. And so there is no influential gender or marital related base interpersonal differences that can affect your data. So this is how you can do it for binary logistic regression. For ordinal and multinomial is a little bit different. For ordinal and multinomial, you don't have a separate different blocks of prediction. You just simply send it to your variable marital status. And remember, it's not just about categorical variables. I can, for example, include age as a covariate as well. But I just, instead of sending to factor, I will send it to covariance. So it's just doesn't matter. So factor just means that they are categorical variables. So in ordinary linear regression, I just put my covariate variables, the variables that I want to consider as covariate, as confounding variables. I just put them as additional predictors here and just click on OK. And here, if I just need to see the results of location for my main variables, that means that they is already accounted for the potential confounding effects of my covariates. And I can also see if my covariates had any effects on my data that I can see, no, they didn't have actually any, there's no interpersonal differences based on this like gender or marital status that can affect the result of my model. And even if they were significant, still they wouldn't affect my result because they are already controlled. The effects is already controlled for that. And that's why I can call for example, like here, when I have odd ratio, I can call them adjusted odd ratio. And I can call this model adjusted model because it's adjusted based after controlling the effects of covariance. And the same for multinomial logistic regression, that I can just add my covariates as additional variables in the model. Like for example, maybe I can even bring them early. And sorry, it's not because they are categorical, actually, I put them in the factor. If they were continuous, like age, I could put it like in here. And then, okay, there are just additional predictors, your covariates, and the effects will be controlled in your study. So for example, I just look for my main variables, and I'm sure that the effects is controlled for the categorical variables. For example, you can see that here, like one of the levels of marital status could potentially actually have an effect on my data. But the good news is that I control that effects, and now I can rest assured that my model is adjusted, my odd ratio is adjusted after controlling for these confounding variables. So that's as easy as that. So I know that it was very long tutorial, and thank you for your attention, but I just wanted to make sure that everything is comprehensive. And maybe just one last point, that if you wanted to go to too much details about like how the categorical variables have its effect, for example, if they are significant, like for example, you see that here, this level of marital status is significant. So if you want to interpret that, you actually can say that the level 1 of marital status compared to level 4 has a significant impact on your, can actually increase the odds of mild depression compared to normal depression. Because it's a covariate, you don't need to go to that level of details, but just wanted to let you know how it's interpreted if you wanted to interpret. For example, imagine that if the level 1 of my marital status is like single and level 4 is like married or divorced, that means that a person who is single actually can have there can be a higher possibility for this person to show mild level of depression compared to a normal level of depression. So it can have a similar interpretation like this, but as you can see in publications, they usually don't go through these details for the covariate variables. They just interpret the main independent variables, saying that the covariates are controlled in the models. So that was all for all types of logistic regression, including assumption checks.